Well, in this video, we're going to look at the covariance of two vectors. And this is a video that will hopefully lead to a discussion of principal component analysis, which is a method used in statistics. And I want to make some videos that go into how principal component analysis works. There are a bunch of videos in principal component analysis on the internet already, but I think that a lot of them just give a very brief mathematical overview, if it does that at all, and mainly just talks about how to do it on a computer and doesn't really get into the nitty-gritty of the math, or at least provides a very fast overview where I'm not really sure if anyone watching it really understands it, and definitely not many examples. So I want to explain it the way that I think is, mathematically rigorous and complete. And to do that, we have to talk about the covariance of two vectors in Rn. So let's say that, so here we have a definition. So, give me one moment. Definition. And I have two vectors in Rn, but I'm actually going to use a capital N because it's more in line with the convention of the data matrix. So if you have these two vectors V, let's say its components are A1 through AN, and W is B1 through Bn, capital N. If V and W are vectors in Rn, then we define the covariance of V and W is, well, it's a scalar. It's 1 over n minus 1 times V dot W. So you take V dot W and then divide it by n minus 1. Okay? So it's almost a dot product. It's just scaled by 1 over n minus 1. And the reason it's for the 1 over n minus 1 has to do with statistics. Okay, we're not going to worry too much about that. The point is that it's pretty much the dot product. And the variance, so covariance is when you have two vectors. If you just have a single vector, the variance of the vector V is just the covariance of V with itself. In other words, so I don't think this is common notation, but I'll use the covariance of V and W to be this. The variance of V is the covariance of V. So in other words, the variance of V is 1 over n minus 1 times the dot product of V and V. So if you want to write it in terms of the components, the AIs and the BIs, this is going to be 1 over n minus 1 times A1B1 plus dot 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 plus ANBN. And then this is the variance of V is 1 over n minus 1 times A1 squared plus dot 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 plus A capital N squared. Okay? And then one thing I want to mention is that this is different than the variance of a random variable. So if you take a course in probability, you might have learned about the variance of a random variable. This is not what we're talking about. This is a different thing. Okay. If you have a sample, like you're gathering data, then maybe the components A1 through AN are the different measurements that you take. And then the variance of the vector v is a measure of how spread out the AIs are. So for instance, if all the AIs are 0, right, if v is the 0 vector, then the variance is 0. Okay? Otherwise, it's some positive number, and the greater the AIs are in general, the greater the variance will be. Right? If they're really positive, really negative, then you get a really large variance. Okay. Now, how is this related to matrices? Well, let's say that you have a bunch of vectors, a1 through an. So let's say that you have this matrix B, and its rows are a1 through an. This is a, say, n by p matrix. B, n rows. Okay. Now let's take a look at, in the examples we'll talk about, we'll think of B as a data matrix. Basically, it's a matrix that you get by gathering data. Of course, you know, that's just the matrix, right? I mean, if you just have a bunch of numbers, data is a bunch of numbers, I mean, you get a matrix. So there isn't anything particularly special about a data matrix. It's just a matrix. But you think of it as a matrix that we get by taking samples of something. That's how it'll be used in applications. So when you take B, okay, let's multiply this by B transpose. Well, recall that the dot product is, if we think of these vectors as matrices, this is V transpose times V, right? That's one way I think of the dot product. So what happens if you do this? You take B and then you multiply by B transpose. Okay. Oh, I guess technically, well, I'll explain what's going on in a minute. So here I have these rows, and when I'm thinking of this V transpose V, I'm thinking of those as a V as a column vector, right? But here I have a row vector, so it's slightly different. Well, okay, so we're going to do B times B transpose. So B times B transpose, well, B transpose will have columns A1 through AN. And now what happens when you look at the IJ entry, the IJ entry of B transpose is just row I dotted with column J of B transpose, right? You take the ith row of B and then you dot it with the jth column of B transpose, and that gives you the product. So I guess these are AI to AN transpose. It's just AI, this vector, times AJ transpose. Right, but that's just going to be the dot product of AI with AJ. I guess to keep in with the notation, it's the dot product of AI. See, I don't want to. Okay, I'm thinking of. I'm mixing up the rows and columns, but it's not really a big deal. The point is that you do the dot product of the ith row in this column, right? I mean, when I was talking about the dot product, when I have the dot product here, I'm thinking of two column vectors, so that's why the notation is a bit messed up. But anyway, I'm just going to write this as AI dot AJ. Okay. I guess AJ, yeah. Okay. So this is the dot product, right? I guess it should be AI transpose it to be super correct. Anyway, well, that's almost the variance. So if you divide by n minus 1, 1 over n minus 1 times b transpose has ij entry the covariance of AI and AJ. So this matrix is called, well, it's an n by n matrix, right? This is a n by p matrix. B is an n by p matrix, so B transpose is p by n. And so the product is n by n. So this is the n by n covariance matrix of B. So if you have a matrix B, you can form a matrix 1 over n minus 1 B transpose, and this matrix has the property that the ij entry is the covariance of AI and AJ. In particular, the diagonal entry, the diagonal entries of this matrix are the variances of the row vectors of B. And we define the total variance so the total variance is the sum of the variances of the rows of B, right? So you take each of these AIs, each of these rows, take the variance of each of those, add them up. That's just the sum of the diagonal entries. So the sum of the variances of the rows of B, the total variance is the sum of the diagonal entries of the covariance matrix. Well, what's the word for the sum of the diagonal entries of a matrix? That's the trace. So i.e. it's the trace of 1 over n minus 1 B transpose. Okay, that's all I wanted to say about this, just to get some definitions off the ground. And we're going to be working with this covariance matrix. One thing you notice is that the covariance of V and W, that's equal to the covariance of W and V. Right? Because you're looking at a dot product. The order in which you do the dot product doesn't matter. V dot W is the same as W dot V. So the covariance of V and W is the same as the covariance of W and V. Well, what does that tell you about this covariance matrix? Right? The ij entry is the covariance of AI and AJ, but that's the same as the covariance of AJ and AI. And so that tells you that the ij entry is the same as the ji entry. And so this matrix is a symmetric matrix. The covariance matrix is a symmetric matrix. And so it has an orthogonal diagonalization, right? It can be decomposed into a product of an orthogonal matrix Q, a diagonal matrix of eigenvalues lambda, and then Q inverse. And we're going to talk about what's the significance of the Q and the lambda and the Q inverse. Well, maybe not the Q inverse, but the Q and the lambda in future videos. And this is going to be related to principal component analysis and what that has to do with variance. Okay, thanks for watching.